Hi, welcome to our channel of IGNOU audiobooks, Indira Gandhi National Open University, School of Engineering and Technology, SOET, Diploma, Postgraduate Diploma Programs, Diploma in Smart City Development and Management, DSCDM, MIO 002 Smart Technologies, Hardware and Software, Block-1 IIOT, IIOT and IOE. Unit 1 Internet of Things, IoT, and its applications. If we had computers that knew everything there was to know about things, using data they gathered without any help from us, we would be able to track and count everything, and greatly reduce waste, loss and cost. We would know when things needed replacing, repairing or recalling, and whether they were fresh or past their best. Kevin Ashton, an expert on digital innovation. The new rule for the future is going to be, anything that can be connected, will be connected. 1.1 Introduction to Internet of Things, IoT. The Internet of Things means taking all the things in the world and connecting them to the Internet. Simply put, this is the concept of basically connecting any device with an on and off switch to the Internet, and/or to each other. This includes everything from cell phones, coffee makers, washing machines, headphones, lamps, wearable devices and virtually any object for which remote communication, data collection, or control might be useful, such as vehicles, appliances, medical devices, electric grids, transportation infrastructure, manufacturing equipment, or building systems. This also applies to components of machines, for example, a jet engine of an aeroplane or the drill bit of an oil rig etc. The IoT is a giant network of connected things, which also includes people, as shown in Figure 1.1. The relationship will be between people to people, people to things, and things to things. Broadband internet has become more widely available, the cost of connecting is decreasing, more devices are being created with Wi-Fi capabilities and sensors built into them, technology costs are going down, and smartphone penetration is skyrocketing. All of these things are creating a perfect storm for the IoT. In other words, the IoT potentially includes huge numbers and kinds of interconnected objects. It is often considered the next major stage in the evolution of cyberspace. Some observers believe it might even lead to a world where cyberspace and human space would seem to effectively merge, with unpredictable but potentially momentous societal and cultural impacts. Two features make objects part of the IoT, a unique identifier and Internet connectivity. Such smart objects each have a unique Internet Protocol, IP, address to identify the objects sending and receiving information. Smart objects can form systems that communicate among themselves, usually in concert with computers, allowing automated and remote control of many independent processes and potentially transforming them into integrated systems. Those systems can potentially impact homes and communities, factories and cities, and every sector of the economy, both domestically and globally. Although the full extent and nature of the IoT's impacts remain uncertain, economic analyses predict that it will contribute trillions of dollars to economic growth over the next decade. Sectors that may be particularly affected include agriculture, energy, government, healthcare, manufacturing, and transportation. The IoT can contribute to more integrated and functional infrastructure, especially in smart cities, with projected improvements in transportation, utilities, and other municipal services. Objectives. After studying this unit, you should be able to define Internet of Things, explain the characteristics of IoT, discuss the physical and logical design of IoT and describe various applications of IoT. 1.2 Definition of IoT. IoT is a ubiquitous network except that all of those electronic devices have access to the Internet. IoT is the concept created around the idea of full ubiquitous computing, which is the processing of information linked with external activity or objects. Ubiquitous computing involves connecting electronic devices with microprocessors and sensors to talk to each other. The Internet of Things, IoT, is a computing concept that describes the idea of everyday physical objects being connected to the Internet and being able to identify themselves to other devices and send and receive data. The term is closely identified with radio frequency identification, RFID, as the method of communication, although it also may include other sensor technologies, wireless technologies or QR codes. The IoT is significant because an object that can represent itself digitally becomes something greater than the object by itself. No longer does the object relate just to its user, but it is now connected to surrounding objects and database data. When many objects act in unison, they are known as having ambient intelligence. 1.3 Characteristics of IoT. The IoT is a complex system with a number of characteristics. Its characteristics vary from one domain to another. Some of the general and key characteristics identified during the research study are as follows. Intelligence. IoT comes with a combination of algorithms and computation, software and hardware that makes it smart. Ambient intelligence in IoT enhances its capabilities, which facilitates things to respond in an intelligent way to a particular situation and supports them in carrying out specific tasks. In spite of all the popularity of smart technologies, intelligence in IoT is only concerned with means of interaction between devices, while user and device interaction is achieved by standard input methods and graphical user interface. Connectivity. In the case of IoT, the most important feature one can consider is connectivity. Without seamless communication among the interrelated components of the IoT ecosystems, i.e., sensors, compute engines, data hubs, etc., it is not possible to execute any proper business use case. IoT devices can be connected over radio waves, Bluetooth, Wi-Fi, Li-Fi, etc. We can leverage various protocols of Internet connectivity layers in order to maximize efficiency and establish generic connectivity across IoT ecosystems and industry. There may be special cases where the IoT ecosystem is built on premises or in an intranet. Connectivity empowers Internet of Things, IoT, by bringing together everyday objects. Connectivity of these objects is pivotal because simple object-level interactions contribute towards collective intelligence in IoT network. It enables network accessibility and compatibility in the things. With this connectivity, new market opportunities for Internet of Things can be created by the networking of smart things and applications. Dynamic nature. The primary activity of Internet of Things is to collect data from its environment. This is achieved with the dynamic changes that take place around the devices. The state of these devices change dynamically, example sleeping and waking up, connected and or disconnected, as well as the context of devices including temperature, location and speed. In addition to the state of the device, the number of devices also changes dynamically with a person, place and time. Enormous scale. The number of devices that need to be managed and that communicate with each other will be much larger than the devices connected to the current Internet. The management of data generated from these devices and their interpretation for application purposes becomes more critical. Gartner, 2015, confirms the enormous scale of IoT in the estimated report, where it stated that 5.5 million new things will get connected every day and 6.4 billion connected things will be in use worldwide in 2016, which is up by 30% from 2015. The report also forecasts that the number of connected devices will reach 20.8 billion by 2020. Sensing. IoT wouldn't be possible without sensors which will detect or measure any changes in the environment to generate data that can report on their status or even interact with the environment. Sensing technologies provide the means to create capabilities that reflect a true awareness of the physical world and the people in it. The sensing information is simply the analog input from the physical world, but it can provide the rich understanding of our complex world. Heterogeneity. Heterogeneity in Internet of Things is one of the key characteristics. Devices in IoT are based on different hardware platforms and networks and can interact with other devices or service platforms through different networks. IoT architecture should support direct network connectivity between heterogeneous networks. The key design requirements for heterogeneous things and their environments in IoT are scalability, modularity, extensibility and interoperability. Security. IoT devices are naturally vulnerable to security threats. As we gain efficiencies, novel experiences, and other benefits from the IoT, it would be a mistake to forget about security concerns associated with it. There is a high level of transparency and privacy issues with IoT. It is important to secure the endpoints, the networks, and the data that is transferred across all of it means creating a security paradigm. Nearly any physical object can become a part of the IoT if it's connected to the internet to communicate, be controlled, or exchange information. Anything from a webcam to a smart appliance that could be controlled with a smartphone app is an IoT device. Even larger objects such as self-driving cars or planes are becoming IoTs, or are at least enhanced by critical IoT components, such as the sensors and actuators mounted on larger ship or jet engines to ensure they are operating efficiently. Most people think about being connected in terms of computers, tablets and smartphones. IoT describes a world where just about anything can be connected and communicated in an intelligent fashion. The IoT has moved far beyond its original emphasis on machine-to-machine, M2M, applications for manufacturing and business and is now within everyone's reach. IoTs are growing at a staggeringly fast speed. There were more than 50 billion IoT devices as of 2020, which are expected to generate 4.4 zettabytes of data, compared to just 100 billion gigabytes in 2013. A 28.7% compound annual growth rate is expected in that number through 2025. IoT devices can gather data from urban and public areas to affect the environment, public safety and resource management. Eventually, whole factories and even cities will become smart, interconnected pieces of the larger IoT system through the widespread implementation of regional sensors. In other words, with the Internet of Things, the physical world is becoming one big information system. 1.4. Physical design of IoT. Two features make objects part of the IoT: a unique identifier and internet connectivity. Such smart objects each have a unique Internet Protocol (IP) address to identify the objects sending and receiving information. Smart objects can form systems that communicate among themselves, usually in concert with computers, allowing automated and remote control of many independent processes and potentially transforming them into integrated systems. The IoT is not separate from the Internet, but rather, a potentially huge extension and expansion of it. The things that form the basis of the IoT are objects. They could be virtually anything: street lights, thermostats, electric meters, fitness tracker, factory equipment, automobiles, unmanned aircraft systems, UASs or drones, or even cows or sheep in a field. What makes an object part of the IoT is embedded or attached computer chips or similar components that give the object both a unique identifier and internet connectivity. Objects with such components are often called smart, such as smart meters and smart cars. Internet connectivity allows a smart object to communicate with computers and with other smart objects. Connections of smart objects to the Internet can be wired, such as through Ethernet cables, or wireless, such as via a Wi-Fi or cellular network. To enable precise communications, each IoT object must be uniquely identifiable. That is accomplished through an Internet Protocol (IP) address, a number assigned to each Internet-connected device, whether a desktop computer, a mobile phone, a printer, or an IoT object. Those IP addresses ensure that the device or object sending or receiving information is correctly identified. What kind of information do IoT objects communicate? The answer depends on the nature of the object, and it can be simple or complex. For example, a smart thermometer might have only one sensor, used to communicate ambient temperature to a remote weather monitoring center. A wireless medical device might, in contrast, use various sensors to communicate a person's body temperature, pulse, blood pressure, and other variables to a medical service provider via a computer or mobile phone. Smart objects can also be involved in command networks. For example, industrial control systems can adjust manufacturing processes based on input from both other IoT objects and human operators. Network connectivity can permit such operations to be performed in real time, that is, almost instantaneously. Smart objects can form systems that communicate information and commands among themselves, usually in concert with the computers they connect to. This kind of communication enables the use of smart systems in homes, vehicles, factories, and even entire cities. Smart systems allow for automated and remote control of many processes. A smart home can permit remote control of lighting, security, HVAC, heating, ventilating, and air conditioning, and other appliances. In a smart city, an intelligent transportation system, may permit vehicles to communicate with other vehicles and roadways to determine the fastest route to a destination, avoiding traffic jams, and traffic signals can be adjusted based on congestion information received from cameras and other sensors. Buildings might automatically adjust electric usage based on information sent from remote thermometers and other sensors. An industrial internet application can permit companies to monitor production systems and adjust processes, remotely control and synchronize machinery operations, track inventory and supply chains, and perform other tasks. IoT connections and communications can be created across a broad range of objects and networks and can transform previously independent processes into integrated systems. These integrated systems can potentially have substantial effects on homes and communities, factories and cities, and every sector of the economy, both domestically and globally. 1.5 Logical design of IoT. In an IoT-based system there are 5 phases of IoT life cycle. Phase 1, create phase, where devices or sensors collect information from the physical, the environment around them. The data from smart connected devices can be used to generate insights that can help businesses, customers and partners. Phase 2, communicate phase, where the data and events generated are sent through the network to the desired destination. Phase 3, aggregate phase, where data collected are aggregated by the devices itself. Phase 4, analyze phase, where, upon further sophisticated analytics, the aggregated data can be used to generate basic patterns, control and optimize processes. And Phase 5, act phase, where suitable actions are performed based on the information created. 1.6 IoT enabling technologies. There are a wide variety of technologies that are associated with the Internet of Things that facilitate its successful functioning. IoT technologies possess the above-mentioned characteristics which create value and support human activities. They further enhance the capabilities of the IoT network by mutual cooperation and becoming part of the total system. There are many examples of what this might look like or what the potential value might be. Say for example you are on your way to a meeting. Your car could have access to your calendar and already know the best route to take. If the traffic is heavy, your car might send a text to the other party notifying them that you will be late. What if your alarm clock wakes up you at 6 a.m. and then notifies your coffee maker to start brewing coffee for you? What if your office equipment knew when it was running low on supplies and automatically reordered more? What if the wearable device you used in the workplace could tell you when and where you were most active and productive and shared that information with other devices that you used while working? The IoT can be applied to things like transportation networks. On a broader scale, smart cities, can help us reduce waste and improve efficiency for things such as energy use. This is helping us understand and improve how we work and live as shown in Figure 1.2. Figure 1.2. IoT enabling technologies. Look at the screen. SAQ1. A. Define IoT. What are the different characteristics of IoT? B. Discuss the physical and the logical design of IoT. C. What do you understand by IoT enabling technologies? 1.7 IoT in healthcare. Remote sensing medical devices have existed for over more than 2 decades, and telemedicine has already been around for a while. The underlying technology has evolved. We have an interconnected network of intelligent devices capable of making decisions, working as groups, and sending information to the cloud, Internet of Things. IoT is slowly getting traction and evolving alongside the new ultra-fast 5 mobile wireless, artificial intelligence, AI, and big data. Combing these powerful technologies with the Internet of Things will likely revolutionize the healthcare industry. IoT in healthcare using 5G wireless and AI could, for example, completely transform the way patients are monitored and treated remotely. IoT will not only help with the patient's health but also improve the productivity of healthcare industry workers. IoT in the healthcare industry is a great example of omnipresent computing. For example, hundreds of intelligent electronic devices can be set up in a hospital to monitor patients' health status 24/7, talk to each other, make decisions, and upload information to a healthcare cloud platform. IoT in healthcare examples. The workable Internet of Things healthcare examples as shown in Figure 1.3 explains how IoT can be used in healthcare effectively. 1. Sensing and uploading up-to-date patient information to the cloud in emergency situations, from the ambulance or even from home. 2. Medical devices capable of performing self-maintenance. IoT healthcare. Devices will sense their own components, detect low thresholds, and communicate with medical personnel and manufacturers. 3. IoT and wearables can help home patients and the elderly communicate directly with a healthcare facility. 4. Telemedicine can be considered a primitive form of an Internet of Things in healthcare example. With IoT, a patient can be observed and in some cases treated remotely through video cameras and other electronic actuators. In healthcare, these devices can gather different patient data and receive inputs from health practitioners. An Internet of Things healthcare example is continuous glucose monitoring for insulin pens that works effectively for patients with diabetes. All these devices are able to communicate with each other and in some cases take important actions that would provide timely help or even save a life. For example, an IoT healthcare device can make intelligent decisions like calling the healthcare facility if an elderly person has fallen down. After collecting passive data, an IoT healthcare device would send this critical information to the cloud so that doctors can act upon it and view the general patient status, see if calling an ambulance is necessary, what type of help is required, and so on. Thus, Internet of Things, healthcare can greatly improve not only a patient's health and help in critical situations but also the productivity of health employees in hospital. Workflows. Process of IoT healthcare workflow. 1. A sensor collects data from a patient or a doctor, nurse inputs data. 2. An IoT device analyzes the collected data with the help of AI-driven algorithms like machine learning, milliliter. 3. The device makes a decision whether to act or send the information to the cloud. 4. Doctors, health practitioners, or even robots are enabled to make actionable and informed decisions based on the data provided by the IoT device. IoT devices in healthcare. Although not all IoT devices should have a sensor, they at least need to have radio and a given TCP/IP address to enable communication with the Internet. As long as a device has access to the Internet. So, every smartphone is an IoT device. A smartphone with the right set of healthcare apps can help you detect diseases and improve your health. Some examples of these are skin cancer detection apps that use your camera and AI-driven algorithms to map holes on your skin. Other examples would be sleep, yoga, fitness, and pill management apps. Still, a smartphone is a smartphone. Monitoring healthcare is not its primary application. A dedicated healthcare IoT device can do significantly more. Smartwatch. Wearables sold at consumer electronics stores come with sensors and an internet connection. Some of them, like iWatch Series 4, can even monitor the patient's heart rate, control diabetes, help in speech treatment, aid in improving posture, and detect seizures. Insulin pens and smart CGM, continuous glucose monitoring. These devices can monitor blood glucose levels and send the data to a dedicated smartphone app. Patients with diabetes can use these devices to track their glucose levels and even send this data to a healthcare facility. Brain swelling sensors. These tiny sensors are implanted within the cranium to help brain surgeons keep track of severe brain injuries and avoid further deathly swelling. They measure pressure on the brain and are able to dissolve by itself in the body without further medical interference. Ingestible sensors. Prescribed medication is swallowed with a tiny digestible medical sensor that sends a small signal to a wearable receiver on the patient, which, in turn, sends data to a dedicated smartphone app. This sensor can help doctors ensure patients take their medication at all times. Smart video pills. A smart pill can travel through a patient's intestinal tract and take pictures as it travels. It can then send the collected information to a wearable device, which in turn would send it to a dedicated smartphone app or straight to the app. Smart pills can also help visualize the gastrointestinal tract and colon remotely. Benefits of IoT in healthcare. Remote patient monitoring. In 2020, experts believe we will start to see the introduction of remote patient monitoring, RPM, thanks to hospital-at-home devices. This will help monitor chronic conditions and elderly patients to support their in-person care. Wearable IoT. Devices can monitor heart rate and blood pressure, sending data in real time to healthcare providers. In the future, we can expect to see the introduction of IoT ingestible devices to provide highly accurate data on patients' insulin levels for diabetics, vitals levels, active infections etc. They currently face many challenges to ensure ingestible are safe to ingest and can continue functioning without losing charge or breaking within the human body. Applications for diagnosis and treatment. We have also started to see the incorporation of AI software within hospitals to improve the accuracy of diagnosis. Google's DeepMind AI software was able to identify breast cancer more accurately than radiologists, proving that doctors must start incorporating these artificial intelligence technologies into their practices or fall behind. Allowing AI to automate laborious processes means doctors can focus more on care advice and treatment. However, the human-like qualities that doctors provide, are reassurance, care and empathy, cannot be replicated by an app. Telesurgery. The technology enables expert surgeons to operate from the other side of the world with highly intelligent robotics connected to the internet. 5G is expected to accelerate the capabilities in telesurgery as it relies on extremely fast internet speed to provide accurate haptic feedback. If there is even a slight delay in what the remote surgeon can feel via the robot hands, there is a high chance of error. It is expected to reduce the second latency period from 0.27 to 0.01 seconds. IoT in the healthcare industry has countless benefits. However, the most important is that treatment outcomes can be significantly improved or maximized, as the data gathered by IoT healthcare devices is highly accurate, enabling informed decisions. Health facilities and practitioners will be capable of minimizing errors because all patient information can be measured quickly and sent to a board of doctors or a healthcare cloud platform. AI-driven algorithms running on these IoT devices could also help make intelligible decisions or suggestions based on existing data. SAQ2. A. Enumerate a few IoT healthcare devices. B. Discuss the benefits of IoT in healthcare. 1.8 IoT in home automation. The concept of home automation aims to bring the control of operating your everyday home electrical appliances to the tip of the finger, thus giving user affordable lighting solutions, better energy conservation with optimum use of energy. Apart from just lighting solutions, the concept also further extends to have overall control over our home security as well as to build a centralized home entertainment system and much more. The Internet of Things, IoT, based home automation system, aims to control all the devices of a smart home through Internet protocols or cloud-based computing. The IoT-based home automation system offers a lot of flexibility over the wired systems. It comes with various advantages like ease of use, ease of installation, avoid complexity of running through wires or loose electrical connections, easy fault detection and triggering, and above and all it even offers easy mobility. Figure 1.5, IoT Home Automation Components. Look at the screen. Overview. Home automation is constructing automation for a domestic, mentioned as a sensible home or smart house. In the IoT home automation ecosystem, devices like light, fan, TV, etc. can be controlled as shown in figure -1.5. A domestic automation system can monitor and/or manage home attributes that are door lighting, climate, enjoyment systems, and appliances. It is very helpful to control your home devices. It's going to in addition incorporates domestic security such as access management and alarm systems. Once it coupled with the internet, domestic gadgets are a very important constituent of the Internet of Things. A domestic automation system usually connects control devices to a central hub or gateway. The program for control of the system makes use of both wall-mounted terminals, tablet or desktop computers, a smartphone application, or an online interface that may even be approachable off-site through the internet. A typical home automation system consists of the following: IoT sensors, IoT gateways, IoT protocols, IoT firmware, IoT cloud and databases, IoT middleware, if required. The smart home components like smart lighting, smart appliances, intrusion detection, smoke, gas detector, etc. are explained below. 1.8.1 Smart lighting. One example of application of IoT is smart lighting. Imagine a room that can sense the brightness in a workspace. On a sunny morning, the building could turn off the overhead lighting in order to save energy. When the clouds roll in, or the sun begins to set, the building would know to turn on the lights in order to maintain a constant lighting level throughout the day. Smart lighting for home helps in saving energy by adapting the light to the ambient condition and switching on, off or dimming the light when needed. Smart lighting solutions for homes achieve energy saving by sensing the human movements and their environments and controlling the lights accordingly. 1.8.2 Smart appliances. Smart appliances with the management are here and also provide status information to the users remotely. Smart washer, dryer can be controlled remotely and notify when the washing and drying are complete. Smart refrigerators can keep track of the item store and send updates to the users when an item is low on stock. 1.8.3 Intrusion detection. Home intrusion detection systems use security cameras and sensors to detect intrusion and raise alerts. Alert can be in form of an SMS or an email sent to the user. Advanced systems can even send detailed alerts such as an image shoot or short video clips. 1.8.4 Smoke, gas detectors. Smoke detectors are installed in homes and buildings to detect smoke that is an early sign of fire. It uses optical detection, ionization for air sampling techniques to detect smoke. Gas detectors can detect the presence of harmful gases such as Colorado, LPG, etc. It can raise alerts in the human voice describing where the problem is. Hyperlocal data is a major upside of IoT sensors. The advent of increasingly accurate home-based sensors is creating powerful results. IoT in the smart home context has other environmental implications as well, as the potential to apply commercial-style building management strategies to homes becomes increasingly feasible. The potential to cut consumers' utility bills, reduce waste, and improve the environmental footprint of individual homes is a highly attractive prospect. The integrated solution is being planned as to create a single platform and interface to manage smart home IoT devices, including heating and cooling systems, PV installations, and battery storage or chargers for electric vehicles. The system will have the ability to determine when people are home or on their way and to adjust the home's temperature accordingly in advance. Additionally, it will use AI to control energy consumption intelligently by methods such as preferentially using self-generated renewable power. Another interesting possibility is using a combination of EV batteries and PV generation to store power, then release it into the grid when prices are favorable. SAQ 3a. Describe the various applications of IoT in home automation. B. Discuss the smart home components. 1.9 IOT in environment. Environmental concerns are playing an increasingly significant role in our everyday lives. Threats such as climate change and rising pollution are becoming more visible. IoT networks allow us to monitor and combat environment pollution as climate change accelerates. The IoT technology can be useful for environmental uses in a number of ways. 1.9.1 Environmental sensors. Sensors can get the job done where people cannot. Deploying sensors to measure elements like air or water quality, radiation, or sensors to detect hazardous chemicals can help track the evolution of the environment. Inaccessible, polluted or uninhabitable spaces can be accessed without risking the health of technicians. Parents of infants with breathing problems and asthma-affected citizens could also receive precise information in real time. Workers that need to operate in hazardous conditions, like mines or workplaces exposed to radiation, can benefit from this real-time environmental data more than anyone. 1.9.2 Energy efficiency. A Boston Consulting Group report determined that ICT enables climate mitigation strategies could reduce global climate change 16.5% by 2020 compared to current efforts. No other climate mitigation strategy is expected to be as effective. These improvements include smart home and smart building energy management, efficient use of home appliances, smart grid devices, asset tracking applied to logistics and smart industrial motors that adapt speed variably to illustrate with only some examples. The applications of IoT in environmental monitoring are broad minus environmental protection, extreme weather monitoring, water safety, endangered species protection, commercial farming, and more. In these applications, sensors detect and measure every type of environmental change. The Internet of Things is one of the biggest enablers of the green buildings movement. The ability to capture and analyze previously dark data from buildings is giving us deeper insight into energy and resource use, and the ability to control the use of those resources through an intelligent building management system is taking buildings to new levels of sustainability. Smart buildings around the world are consuming less energy. In fact, they are creating their own energy through solar panels and other renewable energy sources, and giving back the energy they don't use. Siemens Crystal Building has been dubbed one of the most sustainable buildings on the planet, using intelligent design. 1.9.3 Air and water pollution. Current monitoring technology for air and water safety primarily uses manual labor, along with advanced instruments and lab processing. IoT improves on this technology by reducing the need for human labor, allowing frequent sampling, increasing the range of sampling and monitoring, allowing sophisticated testing on-site, and binding response efforts to detection systems. This allows us to prevent Substantial contamination and related disasters. 1.9.4 Air pollution monitoring. The challenge of pollution isn't exclusively an industrial one. It's estimated that poor air quality costs the global economy $225 billion annually in lost labor income, according to the World Bank. With global urban areas set to expand by at least 2.5 billion people before 2050, the air pollution issue is only going to intensify. A project announced in July 2018 is based on IoT-based solution approach. Fixed and mobile pollution sensors were rolled out across London's streets. 100 fixed sensors were placed in the worst affected areas and sensitive locations. 2 dedicated Google Street View cars roam the city, providing real-time air pollution data on the move. The 2 Google Street View cars take air quality readings every 30 meters with the aim of flagging pollution hotspots by analyzing data trends over years' worth of data. Online maps showing the data in real time give Londoners information on pollution levels at a granular level, enabling people to plan accordingly. This hyper-local pollution sensing has also been tested in Oakland, California and Houston, Texas, and features specially tweaked Google Street View cars equipped with a sensor platform that measures black carbon, nitric oxide, and nitrogen dioxide. 1.9.5 Commercial farming. Today's sophisticated commercial farms have exploited advanced technology and biotechnology for quite some time. However, IoT introduces more access to deeper automation and analysis. Smart farming. Efficient farming has a huge positive impact on the environment. IoT technology is being used to control crop or greenhouse irrigation through sensors. Automatic irrigation in Southern California is being deployed as a way to fight the periodic droughts, providing water according to the conditions of soil. Connected drones are also being deployed in farming. Their spectral onboard sensors help farmers optimize the use of fertilizer and plant protection products besides providing airborne soil condition data to complement soil sensor information. Much of commercial farming, like weather monitoring, suffers from a lack of precision and requires human labor in the area of monitoring. Its automation also remains limited. IoT sensor-based application is shown in Figure 1.6. IoT allows operations to remove much of the human intervention in system function, farming analysis, and monitoring. Systems detect changes to crops, soil, environment, and more. They optimize standard processes through analysis of large, rich data collections. They also prevent health hazards, e.g., E. coli, from happening and allow better control. 1.9.6 Weather monitoring system. Weather variables such as wind speed and direction, air temperature, humidity and rainfall may all be important factors in determining the course of a wide range of events. For example, agriculture has always been heavily dependent on the weather and weather forecasts, both for its control on the quality and quantity of a harvest and its effect on the farmer's ability to work the land or to graze his stock. IoT-based weather monitoring system is shown in Figure 1.7. Water resources generally depend critically not just upon rainfall, but also other weather phenomena that together drive plant growth, photosynthesis and evaporation. Just as pollen and seed dispersal in the atmosphere are driven almost entirely by the weather, so too is the direction and distance of travel of atmospheric pollution. Weather monitoring is also important not just in defining present climate, but also for detecting changes in climate and providing the data to input into models which enable us to predict future changes in our environment. Because of the wide variety of uses for the information, there are a large number of environmental variables which are of interest to different groups of people. These include solar radiation, wind speed, wind direction, barometric pressure, air temperature, humidity and net radiation. The demand for these data, usually on an hourly or more frequent timescale, has increasingly been met by the development and widespread deployment of automatic weather stations, AWSs, over the past 30 years or so. A weather monitoring system, WMS, includes several sensors: temperature sensors, humidity sensors and barometric sensors. A scheduler component is connected to the sensors and triggers the readings of the values of the sensors. The report manager collects the data received from sensors and on request provides a report. The report is displayed on screen by screen manager. Finally, history tracker keeps a log of the historical data provided by report manager. The architecture of WMS is as shown in Figure 1.8. Figure 1.8, IoT-based architecture of weather monitoring system. Look at the screen. 1.10 Sensors in weather monitoring system. Pyranometer. The pyranometer measures solar radiation available at the project site. Their radiance measured by the pyranometer is an indicator of the solar energy available for generation. Generally, a minimum of 2 pyranometers are used in every project. First is installed at a horizontal level to measure global horizontal irradiance, and the second at an inclination, the same as the solar panel inclination, for the measurement of global tilt irradiance. The ground-mounted, also called utility-scale solar power plants, use a thermopile-based secondary standard pyranometer for accurate measurement. Module temperature. The energy output from a solar panel depends on its temperature. Therefore, the measurement of module temperature is important for the estimation of the plant performance ratio. The module temperature is measured at multiple locations in the plants, typically at every block level or more. Wind speed and wind direction. The wind data is very critical for the wind farms because the energy output is dependent on the wind speed. The wind at the solar project site affects the temperature of the solar modules, which in turn affects the energy output. Therefore, wind data is useful for solar as well as wind energy plants. Air temperature and humidity. The ambient temperature and humidity affect the heating of the solar panel and thus affect the energy generation. In wind farms, the heating of the wind turbines is dependent on the ambient conditions. Hence, this data is important for renewable energy plants. Barometric pressure. The barometric sensor is used to measure the atmospheric pressure at the location of the solar and wind energy plant. Rain gauge. The rain gauge measures the rainfall at the project site. The rainfall data helps in better estimation of the annual energy generation. This data is also sometimes used for the insurance of the power plant. Cloud cover sensor. The cloud cover sensor measures the cloud height and cloud base. The presence of the cloud at a solar project site adversely affects the energy generation. The cloud cover data helps in the better estimation of energy generation. There are different types of cloud cover sensors available for use in solar power plants. Soiling station. Solar panels' energy output reduces because of the accumulation of the dust on the panel surface. This loss of energy due to soiling is measured using soiling station. Extreme weather. Though powerful, advanced systems currently in use allow deep monitoring, they suffer from using broad instruments, such as radar and satellites, rather than more granular solutions. Their instruments for smaller details lack the same accurate targeting of stronger technology. New IoT advances promise more fine-grained data, better accuracy, and flexibility. Effective forecasting requires high detail and flexibility in range, instrument type, and deployment. This allows early detection and early responses to prevent loss of life and property. Weather reporting bot. Weather forecasting is an application, technology which will predict the condition of an atmosphere for a given location and time. It is important to track the weather report. Daily convenience. There is some third-party application available for mobile application to track the weather forecast. But it would be better if those applications are wrapped in some messenger platform. This weather bot will help us look for the weather report to get the current and Forecast weather details of a location. It will provide the following details of the location which are provided. Current temperature, max, min temperature, humidity, wind speed. Open the weather bot and start a chat with the bot to get the current or forecast. Weather details. Weather bot will be able to provide the following. Current weather report with respect to the map location. Current weather report with respect to the city. Forecast weather report with respect to the map location. Forecast weather report with respect to the city. Forest fire detection. Forest fires, wildfires, are common hazards in forests, particularly in remote or unmanaged areas. It is possible to detect forest fires, elevated CO2, and temperature levels using Internet of Things, IoT, sensors. You can deploy IoT, satellite and solar sensors in remote areas without the need for internet, cellular, mobile or mains power. When forest fires burn, they emit large volumes of carbon dioxide gas, Colorado too. You can use a network of IoT CO2 and temperature sensors for forest fire detection. IoT sensors can operate alongside satellite and optical detection systems or form a standalone network of sensors near key strategic assets. Existing detection methods such as satellite and optical systems can cover large areas. Satellite systems identify infrared signatures, while optical systems look for smoke plumes. Despite using these systems, CO2 and temperature IoT sensors can offer an inexpensive alternative to help detect forest fires. Remote IoT sensor networks. CO2 and temperature IoT sensors are battery and solar powered, using a combination of low RA WAN and satellite communications to provide coverage even in remote areas. A low RA WAN gateway can provide network coverage for up to 15 km outdoors, while satellite backhaul ensures traffic can be sent back to your monitoring system without requiring mobile or internet coverage. 1.11 Summary. In this unit, we will be discussing Internet of Things and its applications. The Internet of Things means nothing but linking all devices, vehicles, home appliances, wearable devices, and smartphones with the internet through mobile app to get and pass the data, information seamlessly. The Internet of Things plays a big role in smart cities applications. Smart cities are building in India and even everywhere in the world. There is a big opportunity for IoT and its applications in implementation in the smart cities. Various IoT technology applications like IoT healthcare, IoT home and IoT environment have been discussed in this unit. Thank you. Subscribe to our channel for more updates, and we will see you with the next chapter.